Imagine a sponge that soaks up almost all the water poured onto it. Vantablack does the same with light. When light hits its surface, instead of reflecting back, it gets trapped within tiny, densely packed carbon nanotubes, much like sunlight disappearing into a forest. This creates the effect of a black hole on a surface, where objects appear completely flat and featureless, because there are no shadows or contours visible. For example, if a crumpled piece of foil were coated with Vantablack, it would look like a flat, black void instead of a crinkly object. This unique ability makes it useful for reducing stray light in telescopes, improving camera performance, and even in artistic displays to create illusions of emptiness and depth. In science, Vantablack is used primarily in optical instruments like telescopes and spectrometers. For instance, it is applied to the internal surfaces of telescopes to absorb stray light, preventing unwanted reflections that could distort the images of stars and galaxies. This allows astronomers to see faint celestial objects more clearly, improving the accuracy of their observations. Similarly, in satellite systems, Vantablack helps reduce glare and light interference, enabling precise measurements of the Earth's atmosphere and surface. By minimizing reflections, Vantablack enhances the performance of scientific devices, making it essential for applications where capturing precise optical data is critical. To understand Vantablack, we must first explore the microscopic world, where this extraordinary material reveals its secrets. Imagine a forest of carbon nanotubes at the nanoscale, and you have a glimpse of Vantablack's intricate structure. These tiny tubes, with walls just 1 atom thick, possess remarkable properties. Their ability to trap light makes them ideal for creating the blackest of blacks. When light strikes Vantablack, it enters this forest and becomes trapped. Less than 1/100% of light escapes, making it appear as the blackest black. The darkness of Vantablack is not merely the absence of light, but rather its near total absorption. This remarkable property stems from the intricate dance between light and matter within the nanotube forest. Imagine a photon, a tiny packet of light energy, hurtling towards a surface of Vantablack. As it enters the dense forest of carbon nanotubes, it encounters a labyrinth of surfaces. Instead of reflecting cleanly off the surface, the photon bounces between the vertically aligned nanotubes. With each bounce, the photon's energy is partially absorbed by the nanotubes and converted into heat. This process, repeated countless times as the photon navigates the nanotube maze, effectively traps the light within the material. Vantablack absorbs up to 99.965% of incident light, making it the blackest material known. We often think of black as the absence of light, the void left when all colors are gone. But the blackness of Vantablack challenges this notion, pushing the boundaries of our perception and our ability to measure darkness. Traditional methods of measuring color, such as using spectrometers to analyze reflected light, prove inadequate for Vantablack. Its surface reflects so little light that conventional instruments struggle to differentiate it from true nothingness. To quantify Vantablack's extreme blackness, scientists turn to specialized instruments and techniques. One such instrument is a spectrophotometer equipped with an integrating sphere, a device that captures and measures nearly all light reflected from a sample. However, even these advanced instruments have their limitations when faced with Vantablack's near-perfect light absorption. Its ability to absorb stray light makes it invaluable in optical instruments, telescopes, and even in military applications for camouflage and stealth technology. Vantablack in space, a new frontier of exploration. The darkness of space has always captivated humankind, beckoning us to explore its mysteries. Now, with the advent of Vantablack, we have a tool that can enhance our ability to peer into the cosmos and unravel its secrets. Imagine a telescope coated with Vantablack, its interior as dark as the space it observes. By absorbing stray light that can interfere with observations, Vantablack allows for sharper images and more sensitive measurements, enabling us to see fainter objects and study them in greater detail. Satellites and spacecraft often rely on delicate instruments that are sensitive to stray light. Coating these instruments with Vantablack can significantly reduce unwanted reflections, improving their accuracy and reliability. This property could be harnessed for thermal control systems in spacecraft, helping to regulate temperatures in the harsh environment of space. The quest for sharper images drives innovation in optics, from telescopes to cameras. Vantablack offers unparalleled light control, pushing optical boundaries. Imagine a camera lens coated with Vantablack, absorbing all stray light. This translates into images with exceptional clarity and contrast. In telescopes, it reduces stray light, revealing fainter objects. Enhanced sensitivity is crucial for observing distant galaxies and exoplanets. The artist's new black Vantablack in art and design. Throughout history, artists have sought new ways to represent light and shadow, to capture the essence of darkness and depth in their work. Now, with Vantablack, they have a tool that transcends traditional pigments, a black so deep that it seems to defy the canvas itself. Imagine a sculpture coated in Vantablack, its three-dimensional form seemingly swallowed by the surrounding darkness. The absence of reflected light obliterates surface details, leaving only the silhouette, a stark representation of form and void. Painters, too, are exploring the unique properties of Vantablack, incorporating it into their works to create striking contrasts and illusions of depth. By juxtaposing this ultimate black with other colors, artists can evoke a sense of mystery, infinity, and the unknown. Beyond the realm of fine art, Vantablack is finding its way into design, architecture, and fashion. From light to heat. Vantablack's energy absorption. Vantablack's extraordinary ability to absorb light has captivating implications beyond its visual impact. This material doesn't merely trap light, it converts it into heat, opening up intriguing possibilities for energy harvesting and thermal management. Imagine a solar panel coated with Vantablack, its surface efficiently absorbing sunlight and converting it into usable energy. The near-perfect light absorption of Vantablack could lead to more efficient solar cells, capturing a greater percentage of the sun's energy and potentially revolutionizing renewable energy technologies. In electronics, where heat dissipation is a constant challenge, Vantablack coatings could be used to improve the efficiency and lifespan of devices by effectively dissipating heat away from sensitive components. Vantablack's unique thermal properties make it a promising material for developing advanced thermal management systems, enabling engineers to design more efficient and reliable devices that can withstand extreme temperatures. Beyond Vantablack, the quest for darker materials. The creation of Vantablack marked a pivotal moment in material science, demonstrating the ability to manipulate matter at the nanoscale to achieve extraordinary properties. But the quest for darker materials doesn't end there. Scientists are constantly pushing the boundaries of what's possible, exploring new materials and techniques to create even blacker blacks. One avenue of research focuses on refining the structure of carbon nanotubes, optimizing their arrangement and dimensions to further enhance light absorption. By controlling the spacing and alignment of nanotubes, scientists aim to create materials that trap light even more effectively than Vantablack. Another approach involves exploring alternative materials with high light absorption capabilities. Researchers are investigating the use of metamaterials, artificially engineered materials with properties not found in nature, to create surfaces that can absorb light across a wider range of wavelengths. The future of black possibilities and implications. The development of Vantablack and the ongoing quest for even darker materials have opened up a Pandora's box of possibilities, with implications spanning across various fields and raising profound questions about the nature of light, perception, and the very fabric of our universe. Imagine a world where ultra-black materials are ubiquitous, used in everything from clothing that renders the wearer invisible to buildings that disappear into the night sky. Beyond its visual impact, the ability to control light and heat with such precision has the potential to revolutionize energy production, thermal management, and optical technologies. We could see the development of hyper-efficient solar cells, devices that remain cool even under intense sunlight, and optical instruments with unparalleled sensitivity. The potential for misuse, whether for military purposes or for creating deceptive technologies, highlights the need for responsible innovation and careful consideration of the broader societal impact. Vantablack and the wonders of material science. Vantablack stands as a testament to the ingenuity of human endeavor, a material so dark that it challenges our perception of reality and pushes the boundaries of what we thought possible. Its creation is a testament to the power of material science, allowing us to manipulate matter at the atomic level and unlock extraordinary properties. But Vantablack is more than just a scientific marvel. It is a source of inspiration for artists, a tool for exploration for astronomers, and a catalyst for innovation across various industries. Its unique properties have sparked a global fascination with the nature of black, light, and our ability to perceive the world around us. The story of Vantablack is a reminder that the most profound discoveries often lie at the intersection of science and wonder.